So far, all the applications of pH we've seen have been pretty straightforward, and that's because we've only been considering strong acids or bases. Of course, as explained previously, for a weak acid, there's going to be an equilibrium to consider with significant amounts of both reactants and products present. The equilibrium for any generic weak acid, HA, is shown here, along with its equilibrium constant. The equilibrium constant for an acid dissociation is abbreviated as Ka, and is equal to the hydronium ion concentration multiplied by the acid's conjugate base concentration, all divided by the concentration of the undissociated acid itself. Some example values for acid dissociation constants are shown here. For a strong acid, like HCl, Ka can be rather large, into the product favored range of above 10 to the third power, but for most weak acids, the Ka value will be relatively small, definitely less than 1, and usually even less than 10 to the minus 3, making the dissociation reactions generally reactant favored. These values are well established for most acids, and would be provided for you as needed in most cases. It's somewhat common to express, rather than the value of Ka, the value of what's termed the pKa. Just like with the pH, the lowercase p here indicates the negative logarithm of the value after it. In the case of pH, that's the negative log of the hydrogen ion concentration. In the case of pKa, that's the negative log of the Ka value. Larger Ka values are associated with weaker acids, and due to the negative sign in front of the logarithms, smaller pKa values are associated with stronger acids, and vice versa. Okay, let's use one of these values to answer a question related to a weak acid, one where the equilibrium needs to be taken into account. The pH of a 0.250 molar solution of hydrofluoric acid is 2.036. What are the values of Ka and pKa for hydrofluoric acid? You may have heard that hydrofluoric acid is an extremely dangerous substance, which is true, but it's actually not a strong acid, but a weak one. So we'll need to account for its equilibrium behavior using an ice chart. Since water doesn't appear in the equilibrium constant expression, we don't need to include it in our chart. In the row of initial concentrations, we have 0.250 molar for HF. That just comes from the problem. The concentration of fluoride is initially 0, since it's only generated when the HF dissociates. The initial concentration of H3O+ is not strictly 0. Remember, water, before we dissolve any HF in it, has an H3O+ concentration of 1.0 times 10 to the minus 7 molar, but that is typically tiny compared to the amount generated when our acid dissociates, so we can treat it as approximately 0 for most purposes. When the system comes to equilibrium, it will do so by dissociating some HF to form hydronium and fluoride ions. It has to proceed in this direction since there is no fluoride and virtually none of the other product, hydronium ions. Everything in these equilibria occurs in a 1-to-1 stoichiometric ratio, so our HF concentration will decrease by x when it dissociates. Our product concentrations will increase by x. This gives equilibrium concentrations of 0.250 minus x for HF, and 0 plus x equals x for both hydronium and fluoride equilibrium concentrations. Now, what's the value of x? We know the concentration of hydronium ions is x and that the pH is 2.036, as stated in the problem. So the hydronium concentration has to be 10 to the minus 2.036 power, or 0.00920 molar. This then must be the value of x. Let's set up our expression for Ka, which is shown here at the top of the screen. This has the same format for all acid dissociations. We determined that our hydronium and fluoride concentrations were 0.00920 molar, since both were equal to x. The concentration of undissociated HF is 0.250 minus x, or 0.241 molar. Plugging all these values into our Ka expression, we get 3.15 times 10 to the minus 4, and to find the pKa, we just take negative log base 10 of that result, which gives us 3.455. Here's another example of how we can use a weak acid equilibrium. We're asked to calculate the pH of a 0.10 molar hydrocyanic acid solution, an acid which has a Ka of 4.9 times 10 to the minus 10. The Ka value shown on this slide is incorrect. It'll get fixed on the next slide. Of course, our initial concentration of HCN is 0.10 molar, and the hydronium and cyanide concentrations are effectively 0 at the beginning. Our equilibrium concentration of HCN will be 0.10 minus x, and our equilibrium concentrations of hydronium and cyanide will both be x. We can substitute these expressions and 4.9 times 10 to the minus 10 into our Ka expression, and we end up with x squared over 0.10 minus x. In most situations, the x value is going to be much smaller than the initial concentration, so 0.10 minus x should just be about 0.10 itself. The general rule is that if the x value we find is 5% of this initial concentration or less, we don't have to include x in the denominator. If we multiply both sides by 0.1 and then take the square root, we get x, which is equal to the hydronium ion concentration, which ends up being 7.0 times 10 to the minus 6 molar. Since this is less than 5% of 0.10, our approximation in the previous step was valid and we don't need to use the quadratic formula. Now that we know our hydronium concentration, we can use it to find the pH, which ends up being 5.15. Another question you might come across is the notion of percent dissociation of a weak acid. In other words, of the initial concentration of the weak acid, how much is actually dissociated? This is equal to the concentration of the dissociated ions, either the hydronium or conjugate base concentration, divided by the initial concentration of the acid itself, multiplied by 100 to convert it into a percentage. One somewhat counterintuitive result is that weak acids have lower percent dissociations at higher concentrations. While the concentration of dissociated ions, hydronium and conjugate base ions, increases overall as the concentration of a weak acid increases, they do so at a slower rate than the increase in concentration of the weak acid itself. As a result, the percent dissociation drops logarithmically as the concentration of the acid increases. Here you can see that result for acetic acid at various concentrations. So far we've discussed equilibria for acids that produce one hydrogen ion when they dissociate. Of course, some acids can produce two or more hydronium ions when they dissociate. These are referred to as polyprotic acids, as opposed to the monoprotic acids we've considered up to this point. We can see here the example of carbonic acid, H2CO3, which can produce two hydronium ions when it dissociates. And this example illustrates an important point. The dissociation of each hydronium ion needs to be considered separately. In other words, the first dissociation and second dissociation have different equilibrium constants. In the case of carbonic acid, the first dissociation produces one hydronium ion and one bicarbonate ion. Since this is the first dissociation, we can refer to the equilibrium constant associated with it as Ka1, and it has a value of 4.3 times 10 to the minus 7 for carbonic acid. The bicarbonate ion, HCO3-, which is the conjugate base of carbonic acid in the first equation, can also produce one more dissociation, producing another hydronium ion and carbonate ions. This second dissociation, which we can quantify with Ka2, has a value of 5.6 times 10 to the minus 11. This chart shows the stepwise dissociation constants for several common polyprotic acids. While the particular values for these would be provided for you as needed, there is an important trend to notice. Ka1 is always larger than Ka2, usually by at least several orders of magnitude. If there is a Ka3, like with phosphoric acid, it will be even smaller than Ka2. This makes sense conceptually. It should be harder to remove a positively charged hydrogen from, for instance, a bicarbonate ion than it would be for neutrally charged carbonic acid. Another notable feature of this chart is sulfuric acid, which you may remember is a strong acid. This is true, but only the first dissociation is complete. The second dissociation actually behaves as a weak acid. Now, it's not always as complex as it seems. For instance, let's consider this example, calculating the pH of a 0.20 molar carbonic acid solution. Of course, this is a diprotic acid. However, we can simplify matters by only considering the first dissociation and ignoring the second one. Why? Because like most polyprotic acids, the second dissociation is much smaller than the first one. Ka1, with a value of 4.3 times 10 to the minus 7, is almost 10,000 times larger than Ka2, which has a value of 5.6 times 10 to the minus 11. Therefore, we can treat a solution containing only a diprotic acid in essentially the same way as a monoprotic acid. So we set up the ice chart here based purely on the first dissociation and the associated value of Ka1, and we solve for x, which is also equal to the hydronium ion concentration itself, which turns out to be 9.3 times 10 to the minus 5 molar. So to find the pH, we take the negative base 10 log of that number, giving us a pH of 4.03. Besides the assumptions we made in previous weak acid equilibrium problems, namely that we can ignore the 1.0 times 10 to the minus 7 molar starting concentration of hydronium ions, and that the initial concentration of carbonic acid is so much larger than x that we can treat 0.020 minus x as just the same as 0.020 itself, We also assumed that the second dissociation and Ka2 can be ignored, since Ka2 is so much smaller than Ka1. All of these assumptions end up working well here.